Are you dealing with assembly situations in your manufacturing environment? Metrological analysis can be difficult in exactly that context. In many cases, the problem is that there is measuring data available for separate parts, but not for their assembly. This can be due to different reasons. One reason is that it's simply not possible to acquire data from the assembled situation. How can that be? For example, in sand casting applications, the sand molds are destroyed after casting the desired part. And therefore, the assembled situation visualized here cannot be measured. Another reason is that parts are manufactured and measured separately at different locations, but at the site where the parts are assembled, no measurement is possible. Imagine you could get rid of those problems, or at least minimize them. And to do so, it would be great to be able to recreate the physical assembly situation in GOM Inspect, so a digital assembly. And that's just what I want to show you today. Welcome to today's webinar. My name is Fabian von Steen, and in the next 40 minutes I will show you how to master assembly situations in our new software GOM Inspect 2018. In the Q&A section, my colleague Bernd Oerding will answer your questions, so don't hesitate to ask questions during this webinar. Let's get started. In this webinar, we want to focus on assembly situations in primary shaping processes. Primary shaping processes form the basis in many production chains. But what exactly are primary shaping processes? According to DIN 8580, primary shaping is one of 6 main categories of manufacturing processes, besides, for example, forming, joining, and coating. The definition states that primary shaping is the manufacturing of a solid body from a shapeless material by creating cohesion. And the shapeless material used can be in different states. Gaseous or vaporous, like for example for depositing thin films of metal from a vapor phase. Fluid, like for casting. Malleable, like for injection molding, or even ionized, like for galvanizing. Primary shaping processes are a very important category of manufacturing processes because many different materials can be processed, such as metals, plastics, or ceramics. Depending on the material type and state you want or have to use, different methods are used in the industry. Typical applications are sand casting, investment casting, die casting, injection molding, or slush molding. In this webinar, I will focus on the sand casting process. And of course, you can transfer the workflows I use here to your specific application, or like injection molding and general tool making as well. Why did I choose a sand casting process as an example, you may ask? One reason is that there are several different departments involved in such a process chain. For example, the model making department, the core shop, molding shop, and so on. And each of the department is responsible only for a small section of the overall process chain. Therefore, understanding and controlling the whole process step by step is very important. Another reason is that the sand casting process chain consists of several different steps, and each of them using different suitable tools. Those tools are being used in assembly situations to create further tools or the desired product, of course. To guarantee good quality and to realize the desired functionality of those products, it is crucial to analyze those assembly situations. Let's have a brief overview about a typical sand casting process. Basically, our process chain consists of 2 parallel branches. The upper branch is called the sand forming and shows the manufacturing of the sand molds. Basically, the sand molds are designed for creating the outer shape of the cast part. The starting point is a technical drawing or a CAD of the final part coming from a customer, which is then handed to the foundry. The foundry then is responsible for designing a tool for mold production, so-called patterns or pattern plates, which are the positive of the final cast part. This tool includes casting specific information like shrinkage factors, gating system, draft angles, and so on. And in our case, this kind of tool is CNC machined or created by CNC machining. This is just an example. The pattern plates are then used to form the sand molds, which is done in an assembly. The lower process branch is the so-called core shooting and shows the manufacturing of the sand cores. And again, the sand cores are needed to create the hollow structures and undercuts in the cast part. And again, starting point is the technical drawing or the CAD of the final part, and then the foundry is responsible to design a tool which is able to create the sand core. And this tool is called the so-called core box and consists of two parts in our example. Then the core box halves are assembled on a so-called core shooting machine, and the cavity built up by those two core box halves is filled up with sand then. And this sand is a sand resin mixture, and into this sand resin mixture a catalyst gas is fed into harden the sand. Later, during the demonstration, we will focus on exactly that part of the overall process chain of the sand casting process. So let's have a look at this in more detail. Here you can see a typical core shooting machine. Here the core box is clamped on the core shooting machine. You can see this is an assembly situation of both core box halves, and the worker has put the sand resin mixture on top of the machine into the so-called sand bunker, and the next step is to fill up the cavity built up by the core box with sand, and this is done with very high pressure, leading to a compaction of the sand. Now the catalyst gas is fed into the sand resin mixture to harden the sand. So after a couple of minutes the sand is hardened, and this is the next step is then to open the core box to get the final sand core. Here you can see typical reference points on the core box parts. With these reference points, it's possible to measure the position of the core box halves against each other using an ATOS measurement. But in this situation, it's difficult to reference the sand core in the core box assembly, so this has to be done in a digital way, reconstructed in a digital way. So the last step is some manual deburring here to improve the surface quality, and then we are done with the sand core. Now sand molds and sand cores are manufactured, and of course we want to cast the final part, which is in our case valve housing. And the first step is to put two sand cores into the lower sand mold. This is because we cast two identical parts per run. After that, the upper sand mold is put on top of the lower sand mold, and this assembly situation here can be measured using a tri-top measurement. So we have an assembly situation of a lower sand mold, an upper sand mold, and two sand cores, and this can be done using this can be measured using a tri-top measurement and transforming the scans after that via common reference points. After the assembly, or after creating the assembly situation, the liquid metal is poured into the cavity of the sand mold, leading to the final casting. And after solidification, the sand molds are destroyed to reveal the cast part. So the assembly situation of the casted part plus all the sand mold parts is not possible to measure because we are destroying some of the parts. So what have we learned from it? Simply spoken, we are dealing with a lot of parts and assembly situations which must be analyzed in order to fulfill customer requirements. Some of those assemblies you've seen can be measured using common reference points in an ATOS or tri-top measurement, but some of them can't. However, to provide high quality in the final product, understanding and controlling the overall process is a must. And to achieve this, we should at least be able to analyze all assembly situations. And this leads us to the part-based workflow of the GOM software. To work with a part-based workflow in the GOM software, you have to create a new project of the part project type. The new part project type is accessible via the File menu, choosing New Project Parts. On the right-hand side, you can see typical situations of a part project. It's an explorer of the GOM Inspect software filled with different parts already. And now we want to have a closer look on what a part project is and what kind of benefits come with it. In a part project, it is possible, of course, as the name suggests, to create parts, like here the lower pattern, the lower sand mold, and the raw casting. And each of these parts can hold a nominal and an actual data set, as well as typical constructions, inspections, and alignments. So one typical scenario to use such kind of project is, for example, to merge projects with inspections of individual parts into one common project file. But the interesting thing here is not to do inspections of separate parts, but to be able to do interpart inspections as needed in our assembly situations. But before doing such interpart inspections, an appropriate alignment of the parts against each other is needed. And this leads us to the next topic, alignments. In a part project, you can either perform a traditional alignment and align the actual data of a part to its respective nominal data. So this can be done for each part, of course. The second point, or the second type of alignment which is possible in a part project, is an interpart alignment. And this means that you can align the actual data of a part A against the nominal data, or even against the actual data of a different part B. And this offers a broad range of new possibilities for inspection. Let's have a look at some situations where a digital assembly using an interpart alignment is beneficial. So what is a typical workflow to measure and inspect assemblies? In an ideal world, first you would scan every part separately, acquiring all the surface details of each part. Then you would do a reference point measurement of the assembled state and transform the scans of the separate parts via common reference points. Thus you measured the real assembled situation. After that, you could do the inspections of each separate part against nominal, and of course to do the same for the assembly. So if you can measure and inspect everything with GOM products, everything is fine. Why do we need the part projects then? The answer is because the workflow described above is not the real world. In the real world, you are facing different problems. One problem is that you don't have the CAD for some parts and thus have no CAD for the assembly. This is the case, for example, for the sand molds in our sand casting process. So how do you assess the quality of the sand mold or of the assembly situation then? A solution could be to use an interpart alignment of the sand mold against its tool, namely the pattern plate, and inspect it. Another problem might be that the assembly cannot be measured. In the sand casting example, this is the case for the final assembly, meaning the assembly of molds, cores, and the cast part, as visualized here in this image. As we know already, the molds and cores are destroyed to remove the casting, so it's not possible to measure this. A solution to be able to do an inspection might be to align these parts digitally. You learned a little bit about the part projects in theory now. So it's time to take a closer look at an application where the part concept comes into play, namely the core shooting process chain. On the one hand, I will discuss typical problems which can arise in such a process, and on the other hand, I will investigate the root causes for those problems. To do this, we analyze the core shooting process step by step. The final product in the core shooting process is, of course, the sand core. And for the sand core, a CAD is available, so we are able to compare the measured data against nominal, thus doing a classical inspection. Since we want to use the sand core in an assembly situation later, I will create a part project for this. So let's get into the software. So this is the welcome screen of GOM Inspect 2018, and now I will create a fresh project, parts. And the first step is to import data of the sand core. So I will start with the CAD via drag and drop into the Explorer, and now you can see that you have different options, and I will choose the new part option to create a part. So the CAD is imported now, and then I can rename this to an appropriate name, sand core, and the next step is to import the measured data, again via drag and drop, and now I'm choosing the option add to part, and this adds the measured data to this some kind of container or node into this hierarchical tree structure. So the next step, or the first step before doing some inspection, you create an alignment. So I will choose a typical pre-alignment here with a search time short. This is enough in our case. And now we are fine. And I could do a simple inspection like a surface comparison on actual, making this exclusively visible and adjusting the legend to be symmetric. You can see that there are some deviations from nominal. So if you have a closer look here at the so-called core mark, you can see that we have some undersize here. So we have the radius of this core mark is too small, and it's too short in Y direction. And the same holds for the other two core marks. They are too short in Y direction too. And we have some defect or deviation in the center part of the sand core. Let's summarize what we have done so far. You have seen how to create a part in a part project and how to do a typical surface comparison. So this is a simple inspection. And as a result of this simple inspection, we see that the problems are at the core mark regions and in the center of the sand core. The next step is that we want to find out the cause for these deviations on the sand core surface, and therefore we investigate the process step responsible for the sand core production, the core shooting itself. During the core shooting, both halves of the core box are assembled and clamped on the core shooting machine, and then the sand is shot into the core box using high pressure, resulting in a compaction of the sand. The sand is then hardened using a catalyst gas, and now we want to analyze the assembly of core box and sand core. The relative position of the core box parts against each other is known. As I already told you, we used reference points for this to be able to transform the scans into one common coordinate system. This is visualized here using different colors for the meshes, and nevertheless the assembled situation of the sand core to the core box has to be reconstructed digitally. So this couldn't be measured, so we have to recreate the assembly situation in our software. And let's have a look at this. So we again start from the project we created in the last step, and now I will import the meshes or the scan data of the core box parts. The first step is to create a new part for the first of the halves of the core box, so I call it core box left, and the next step is to import the other half. Again, I choose new part, so I will call it core box right. And as you can see here, the position of both core box parts against each other is already correct. We measured this position, and this assembly situation is used in the core shooting process. So we don't want to destroy this assembled situation because this is used in the real process. But we also want to assemble the sand core with the core box, and this is the next step we want to do. And therefore I will use first of all one of the parts of the core box left. And as you can see, we have here the sand core shape, and I will use a pre-alignment for this, and now we are doing an interpart alignment. So we will focus on this part of this dialog of the pre-alignment, and you can see in the part project there are new parameters available. The first one is the parameter part. So here you can choose for which part you want to create an alignment. And you see here this checkbox target element. Here you can choose against which part you want to align the desired part. And as I told you, or if you could imagine that, we want to align the core box against the sand core. And now this button comes into play, invert surface direction. What does this mean? The shape of, or the surface normal of the mesh here, or of the part forming the sand core, points in the opposite direction than the surface of the sand core. So the algorithm tries to bring those surfaces into contact, tries to fit them, and we know that the tool and the sand core itself have surfaces with normal directions which are pointing in opposite directions. So this is why we activate this button here. And the next step was to set the search time to long. And now we are done with the alignment. Again, I will activate the sand core. And you can see that the left core box part is aligned against the sand core nominal now. If I make the other part of the core box now visible, you can see that we destroyed our position or the assembled situation we imported or which we measured. And this has to be fixed now. And this is done by an additional alignment of core box right. So I will choose as an alignment the initial alignment, copy alignment as initial alignment. This is a new alignment type available. And now what we do now is to recreate the original alignment of both core box halves by copying the transformation matrix of the alignment of the core box left part against the sand core nominal to the core box right part. So first of all, we choose what kind of alignment we want to copy. We want to copy the alignment of the core box left, and we want to copy it to the part core box right. So now you can see that we reconstructed our measured assembly situation, and I made the actual data of the sand core visible, so we recreated our assembly situation. So the next step is we want to assess the quality of the tool. So we want to visualize the gaps between the sand core and the core box, and therefore I will use a new function which is called surface distance, and therefore I will select all points on the surface of the sand core, and now I want to measure the distance between the surface of the sand core and a target element, which has to be chosen here in the drop-down menu. And now I want to measure the distance between the sand core and the core box left. And I have to be careful with this invert surface direction button again, because the surfaces or the normals of the surfaces are pointing in opposite direction, because we're dealing with a tool and a product which is created by the tool. So now you can see that we have visualized this surface distance, and I'm pressing the Alt key to keep the selection and press Create. And then I create the same for the surface distance between the sand core and the right core box. And as you can see here in the core mark region of interest, there's no gap, but we still see this surface defect here in the middle or in the center of the sand core, meaning that we have a gap here between the sand core and the core box. So let's summarize. You have seen how to do an interpart alignment and how to apply this interpart alignment to another part. In our case, this was made because the relative position of the halves of the core box has been measured and consequently is known. Then we used the new function surface distance to assess the sand core shape with respect to its tool. If you compare the deviations to nominal on the left hand side to the surface distance to the core box on the right hand side, it is obvious that the surface defects in the center are not caused by an incorrect shape of the core box. So this is a typical core shooting error, meaning that during the core shooting there was no sand, or no sand reached this region. So we have some undersize here. What about the too small core mark? This defect is not visible with respect to the core box, meaning that the tool works correctly here. And this also means that the tool, namely the core box, has to be defective. So let's have a look at the core box in the next step. Therefore, we will compare the measured data of the core box against its CAD file. So in the process chain, the core box manufacturing is in the highlighted position here. And the nominal data of the core box is available, so we can use it for analysis. And for convenience, we will focus only on one of the halves of the core box here. Let's get into the software. So again, we use our already created project, and then I will import the CAD file of one of the core box halves and add it to a part via drag and drop into the Explorer. And I will choose the core box left. Okay. So now some recalculation takes place. Okay, so I will make only the core box left exclusively visible. And the next step is that we want to align the actual data against the nominal data using a local best fit. And for the local best fit, I will only use the shape which is responsible for creating the sand core, meaning this kind of shape here. And to select the region, I will use another part and the function select by mesh. So I will open select by mesh, and I use the sand core, meaning another part, a different part, to select regions on the desired part. So this is very helpful to make selections very, very quick. So now I want to do a main alignment using a local best fit. And now we have to be careful with the target element. Okay, we want to align the actual data of the core box against the core box left nominal. Okay, this is correct. And in this case, the invert surface direction button is deactivated because all the surface normals are pointing in the same direction. Okay, now we are done. We have created our alignment, and again we could do a surface comparison on actual then. So as you can see, we have too much material in this core mark region, and we have some wear out here at the fed of the core box, which is caused by the sand which grinds this material away during different filling steps of this core box. So let's summarize again. In the surface comparison, you can see that there's too much material, as I already said, on one of the core marks, and of course you can see the wear out effect. And if we want to summarize the results step by step again, we first did a classical inspection of the sand core against its nominal, and we saw that the sand core is not okay, especially with respect to the core mark regions and the center. In a second step, we recreated the assembly situation of core and core box in a digital way because we could not measure it. And then we found out that the core box as a tool works correctly with respect to this core mark region here. We found out that the problem with the center still remains, meaning that we have some core shooting error here. And at last, we did a classical inspection again, and comparing the core box to its nominal, and the results show that the core box is not okay again with respect to the core mark. These types of analysis are a very powerful tool to establish process and quality control, and can be easily realized in such kind of part project. To give you some outlook, besides the core shooting process, you are able to analyze all the remaining process steps, like for example the sand molding process. Using a digital assembly here, you can create an assembly of upper and lower pattern plate, for example, to predict casting defects such as shifts, for example. Or you can analyze if damages on the molds are likely to occur during demolding by inspecting the draft angles. So this can be done in the sand mold and pattern plate assembly. Another example of using part projects is to analyze the core clearance of the sand cores inside the sand molds. And the position of the sand core inside the sand molds is crucial for the quality of the product, especially for the wall thickness. Therefore, we inspect the assembly of both sand molds and sand cores, for example. If you want to learn how to do all these inspections, please visit our training course about optical quality control and sand casting processes. Let's summarize what we learned in this webinar. In general, you have seen how the part-based workflow works in a primary shaping process. I discussed different problems during measuring and inspecting assembly situations and how to address them with a part-based workflow. As an application example, I chose a section of a sand casting process chain. Application-specific details were covered very briefly. If you are interested in sand casting, feel free to attend our training course about that topic. You have seen what the main benefits of part projects in GOM Inspect are. Parts offer new ways of doing inspections, like interpart inspections, meaning inspecting one part against another, and interpart alignments allow to predict and reconstruct assemblies. Basically, working with scanned parts belonging to an assembly is more natural, since you can merge them all into one project now and do all the inspections needed. Of course, there's a lot more to discover, for example in other applications which are not covered here, so feel free to try it out yourself. If you want further information about the digital assembly in GOM Software 2018, please visit our YouTube channel. There we prepared videos, e.g. for the handling of multiple parts in GOM projects or about how to use interpart alignments. On our YouTube channel you can also find recorded webinars as well as tutorials. And we also offer a GOM service area where you can find all the manuals, a knowledge base and a lot more. That's it from my side. Thank you for your attention. If you have further questions, my colleague and myself will answer them in the Q&A space for a couple of more minutes.